or what is the relationship or what is the effect of 3D reconstruction algorithm and the weights used in the 3D reconstruction algorithm. So let us take our favorite structure. I mean any one, but this is one that we have been using for the whole course. So let us open this slice. We see some high frequency details, these small spots there, for instance, and we generate projections. So let us look at the projections. This is not what I want. We can see the projections, and each one of the projections, they have a rotation matrix attached. So this is the relationship between the 3D structure and the projection direction, and then we exploit that information to make a 3D reconstruction. The 3D reconstruction, it looks good, and in principle we should recover even this small I have many more things open, so let me close everything. And yeah, so this was the original slice, this is the reconstruction. So even these small spots, they are recovered. There is a little bit of low pass filter, but this is normal because we don't have infinitely many projections. Okay, so the problem is that normally we don't have such a clean case, so we have noise, and here I have added very little noise so that the signal to noise ratio is still very good, and then we have to reconstruct, and we have to estimate the angles and reconstruct. So when you estimate the angles, so we see that the reconstruction still is pretty good, but we will pay attention to the details of this reconstruction. So we can compare this one with this, and what we see is that there is noise. Also there is a loss of reconstruction, of resolution, and we may think that this is related to the fact that we have to estimate the angles. But actually that is partly true, so you can make mistakes in the estimation of the angles, but other part of the problem is that maximum likelihood algorithms, they allow the images to be in multiple positions with different weights. So ideally we would like that the correct position is given weight 1, while all the other possibilities, they are given really low weights. But this is not actually the truth. So what happens is that many of these images, they are given one position, but also they can occupy other positions with a significant weight. So actually Reliant reports the number of projection directions for which this image has a significant weight, and it is 2, 5 for this. We can compute the histogram of this thing. So if you compute the histogram, what you see is that most of the images, they get 4 values, so 4 possible locations with a significant weight. Only a few get 1, and then even this is kind of extreme, but some of them, they may get up to 20, and this distribution also depends on the level of noise. So if you have more noise, it may extend even further. So the thing is that most of the particles, let's say that in these 4 positions, one of them is correct. So that is the correct one, that is the one you should use. The other 3 are totally incorrect, or is at least slightly correct. So slightly incorrect means blurring. So if I put the same projection into different orientations around the right position, what I'm doing is a little bit of blurring. So this blurring, part of it is transferred to this blurring in the 3D reconstruction. How can I know that? Because if you use same angular assignment, so particles are allowed to have from 1 to 20 positions, but it reports the best position, so that we only keep the best one. So if we now use only the best one, now the 3D reconstruction looks different, you see. So it looks pretty different from the one that we have reconstructed. Let us close this. So from the one we have reconstructed using the 20, this one is also filtered, so let us filter to the same resolution as the one of the Reliant Auto Refine, so we can filter it. And now if we open the 16, we can close already this one. This one is the filter version of this one to the same resolution as the reported. And now we can compare these two. And these two, you see that there are differences. So the main difference between these two reconstructions is this one is using every image only once with weight 1, while this one is using every image with multiple locations, different weights, of which one of them might be correct and the other, the remaining, will be surely incorrect. So this surely incorrect makes a little bit of a difference. One may argue, okay, it doesn't matter, because actually even if there is a little bit of blurring, we don't care, because let me close everything, because when we open, for instance, this output here, I'm putting a threshold. So if there is a little bit of blurring, I can very easily get rid of the blurring by increasing this threshold, and then I don't see the blurring anymore. So blurring is a low frequency thing. I don't care about it because of this threshold. But this is not totally true. One can compute the difference between the reconstruction done with all images having multiple locations and all images having only one location. And if you compute the difference is not only low frequency. Actually, the difference has high frequency and has many structural details. So all these structural details are different in the reconstruction with multiple locations compared to the reconstruction with only one location. So it is not something that you can get rid of simply by the threshold, but you're causing small differences in the details. On this branch, what we have is a different issue. So this different issue, what we are showing is that the 3D reconstruction algorithm itself can cause quite a big difference in the quality of the 3D reconstruction. So normally all refinements, they use the Fourier gridding algorithm, in which we are filling the Fourier space with the projections, and we follow the central slice, or we exploit the central slice theorem for that. And as we have seen, given that set of noisy images, we get this kind of of reconstructions. They are noisy, we have to filter them. But if you use a different algorithm, and here there are big differences in time. So this takes a couple of minutes, this takes 90 minutes, so that there is no free lunch. Actually, now this is a CPU implementation. We have now a GPU implementation, but this is very recent, so we don't I'm not showing these results now. So but for instance, if we go to the same slice, so this is slice 116, you can see that there are big differences depending on what is the algorithm that you use for reconstruction. So the algorithm itself can induce quite a big change in the structure. Especially you see here that there are kind of, again, low pass filter signal on top of the small details. Here it is not the case. So there is no free lunch, or there is nothing that doesn't have an impact in the final result. All the algorithms that you are using, they all have an impact in your final structure. This would be all for the exploration of weights and 3D reconstruction. See you in the next project.